Jumping into the EML projects, we have Faucet, an interactive educational virtual reality tool to aid anatomy education with regards to the pterygopalatine fossa, an important superjunction of nerves and blood vessels in the skull.
Hello, I'm Julia. I'm the project lead for Faucet, and that's what we're going to be talking about next. So the principal investigator for this project is Dr. Paul Kindler, UBC Faculty of Medicine, and the EML team responsible for the development during the semester was Dante, the technical lead, myself, the project lead, and Francis Sin, a work learn, and the lead developer. And our volunteers, Rosaline, Pedro, and Hala, were responsible for development and documentation. So the subject matter. This is an anatomical visualization application for visualizing the pterygopalatine fossa, which is a superjunction of nerves and blood vessels in the skull, and it plays a critically important role in supplying the sensory innervation and the blood to several regions of the head, including all upper teeth and related gingivae. It is notoriously hard to visualize in a 2D format, and it's called the Fort Knox of the skull. But this semester was a little different as we diverted from the subject matter itself to work on issues like accessibility and optimization. Accessibility more so to deal with the pandemic conditions that we are currently in. Originally, this application was intended to be used live in lecture with the PI, Powell, Dr. Kindler, using the headset, but last couple of semesters, we pivoted to VR 360 YouTube videos. And this semester, we're trying to find a middle ground between a live use case versus COVID safe conditions. So we attempted to make live stream possible to Microsoft Teams. I'll let the other members talk about the optimization of the existing code base, as Faucet has been attached to EML for quite a while now. So I'll hand it off to them.
Hi, my name is Dante, and I was the technical lead for the project this term. I worked on implementing a way to stabilize the head movements of the user in VR so that any attached user interface elements move in a way that's smooth and comfortable for someone who might be watching the VR experience live streamed. We will talk about the streaming aspect later, but the stabilization system was implemented using a physics simulation component known as a rigid body. The images on this slide show the development process. At the top, we have a before, where I had a stabilized placeholder component. Then we have the way the label system looked before in the middle. And then we have a state diagram showing the desired behavior of our label system. And finally, a final product picture where you see the orbital label being displayed on a user interface element. Now Rosaline will talk about her experience developing the label system.
Hi, my name is Rosaline, and this term I worked on a dynamically resizing labeling system for the Faucet finders. In order to implement this feature, I first created a simple state diagram that attached this functionality to the meshes. One issue with this original implementation was that long names could not fit into the label box properly. Therefore, I added a feature to adjust the box size dynamically according to the length of each inputted name. I've also been working on updating the technical documentation to reflect these changes. The greatest challenge I had as a new member of this project was orienting myself in such a big code base. With the help of existing documentation, however, I was able to understand the inner workings of the project eventually.
Hey, hi, I'm Francis, and I'm the developer for Faucet. My primary contribution to the project this term was the implementation of the scene transition UI, as well as accompanying technical documentation. In previous implementations, users were only able to traverse through the animation sequentially without being able to skip multiple animations at once. The scene transition UI addresses this problem by allowing users to choose whether they want to start with the animations from phase 1 or phase 2 of the project, and to allow them to transition between the two. It incorporates elements like hover effects and fade transitions to improve the usability of this feature and to improve the overall user experience. Given the complexity of the project, it wasn't straightforward how we would incorporate this new feature into the existing implementation, but we eventually decided to reference and reuse elements of the radial menu, which was implemented in previous terms and is shown at the top of this slide for the basic functionalities of this new interface. And as you can see, the design of this UI can be improved in the future. One suggestion is to experiment with the placement of the buttons so that they don't get into the way of the user when they're watching the animations. Next, Pedro will talk about his experience working on the scene transition UI.
My name is Pedro, and I started working with Faucet Finder from the beginning of this term. I worked at the scene transition UI alongside with Francis and with the supervision of Dante and Julia. And my main task was to build change the materials of the buttons on the scene transition UI and finish the schematic for the whole project and add the scene transition UI to the diagram.
Hello, my name is Hala. I started working with the team on Faucet Finder very recently as a volunteer. I was assigned to curate and design a user guide to streaming Faucet Finder. The streaming of multi-display was essential so that the user can easily navigate with the interface while giving the students an optimal 3D experience. This can be done with a second camera that outputs a second display, a stabilized feed with the instructor's head movement. The user guide included a step-by-step IQ5 process of the stream on OBS, which is an open source, powerful, and flexible platform. My approach was to explore the Faucet Finder multi-display and OBS streaming while documenting the process. The biggest challenge was the fact that I had a young experience with such a mature and complex project, but eventually that seemed to have worked out very well since I was able to empathize with a user that's totally new to the project and capture a repeatable and intuitive process.
It's great to see all the progress this term. Thank you so much, guys. Next up, we have the 3D Ancient Athens, a simulator that aims to reconstruct the historical city to bring an immersive experience of buildings in ancient times, allowing for interactive asynchronous teaching, ultimately improving the quality of learning for students. Trigger warning: if you are prone to motion sickness, please be aware of the following video.
Hi, and welcome to the 3D Ancient Athens project. I'm Kevin Fisher, a professor of archaeology in the Department of Classical, Near Eastern, and Religious Studies in the Faculty of Arts and the PI on this project. As an archaeologist, I'm interested in the social dynamics of past-built environments, especially ancient cities, and the application of digital technologies to recording, analyzing, and visualizing archaeological phenomena. I teach a course called Temples, Tombs, and Tyrants: Introduction to the Archaeology of the Middle East, Greece, and Rome. It's a survey course that introduces students to the practice of archaeology in the Mediterranean and Middle East today, and surveys the civilizations of this region from the first farmers to the Roman Empire, covering some 10,000 years of the human past. We're interested in using the archaeological remains of these various civilizations as a way to illustrate and understand the significant social, political, economic, ideological, and technological changes that have occurred over this long period of time. Athens, as a key center in the development of art and architecture, democratic government, philosophy, science, and literature and performance, plays an important role in this class and a number of other classes taught in my department. Two-dimensional maps, plans, and reconstructions used in lectures and textbooks, however, fail to convey the important spatial relationships among various buildings and the city's highly varied landscape and how these change through time. This project aims to develop an application for teaching and learning that would allow both students and instructors to visualize the monuments and other archaeological sites of ancient Athens in 3D in their georeferenced topographical context. They will be able to move about the city and its ancient sites and see them in 3D from various perspectives. They will be able to access additional information on each monument or site, including brief descriptions, historical timelines, current photos, references, and other media. Ideally, this app could serve as a template for other important sites frequently covered in my department's courses. I was lucky enough to work with EML on a visualization application for my archaeological project in Cyprus, and I knew that they'd be able to set me up with a great team that could handle both the technological and pedagogical challenges of this project. So with that, I'll turn it over to the team to tell you about their exciting work.
Today I will be presenting the Ancient Athens simulator. So a little bit about me. I'm a COGS 402 student. My name is Hansen, and I've been working on this project for my capstone project. This program is meant to be a teaching tool that simulates the ancient Athens from historical eras. In this presentation, I will be going through the basic controls and followed up by a video demonstration. For this project, we've decided to go with a WASD scheme where we have two different modes, the bird mode and human mode, and the controls should be the same throughout both modes. The only difference is in bird mode, you're capable of flying, so flying forward will allow you to navigate forwards and ascend upwards or downwards depending on the direction that your camera is facing towards. So here we have the default starting mode. Users will start out in bird mode. And here in the top right corner, we have human and bird mode. The reason why we have two different modes is to allow users to gain a different perspective on things. In bird mode, users will be able to fly freely around the map and see things from different height, as high as they wish, or as low as they wish. And they can see around monuments from different perspectives and angles. And whenever users are ready, they can switch to human mode, which takes the perspective of simulating a human on the ground level. This allows users to get a scale perspective on things, allowing them to view monuments as if they were on the ground, to see how large the monuments are in relation to themselves. This also allows users to get an idea of the scale of the topography, how large the city can be, and allows users to explore the city as if they were in the city themselves. And by freely changing between the modes, users can explore the city from different perspectives in real time. And the other mode will always follow them close behind. For example, if I'm in human mode, the bird mode will always be directly above the human whenever you switch. So you can always pick off where you are from a different perspective immediately. And if you want to go back to ground mode, the human mode will always be ready right below. So we've developed a proof of concept of the UI to show a demo on how learning might take place in this program. So currently we have a menu on the left side. There's only one item at the moment, but going forward, this menu will eventually be filled up with multiple functions that will suit the needs of the students. For example, if the professor wants to attach readings to this program about certain locations, those readings can go into this menu. All it takes is a simple click, and then the reading will come up here. It's draggable throughout the map, so users can drag it to one side while exploring the map at the same time. If the diagram's too small, users are able to enlarge the diagram, as like so. And this way it's non-intrusive and users can pull up the readings while viewing ancient Athens at their own leisure.
Amazing work, guys. I'm really looking forward to seeing more of the city in detail for the future. Again, if you have any questions, you can leave them in the chat now and we will answer them all at the end. So presenting next is the 3D Metabolism team. The 3D Metabolism Project offers a novel way to visualize information contained in a metabolic network in 3 dimensions, making it more convenient to teach and easier to understand.
Okay, hi everyone. My name is Lindsey Rogers. I am a faculty member in the Biochemistry and Molecular Biology department, and I'm also a faculty in residence at Emerging Media Lab. So the project that I'm going to introduce today, our team is really interested in using emerging media to represent and visualize complex networks. And I am a biochemist, and the complex network that we are aiming to represent using emerging media is cellular metabolism. So for some of you who are not biologists, we define metabolism as the entire complement or the entire set of chemical reactions that exist within an organism. So as you can imagine, organisms are really complex, and if we sort of reduce life to the chemical level, there are thousands of metabolic reactions that occur in a coordinated way to enable basically all physiological processes. So if we look at this figure over on the left, this is known as a metabolic map, and we can see lots of metabolic activity within this metabolic map. So from your perspective, you can see lots of lines and dots. The lines represent chemical reactions, which we term metabolic reactions, and the dots represent specific chemicals. In metabolism, we refer to them as metabolites. And often in metabolism, we group lines and dots, or these metabolic reactions and metabolites, into what we call metabolic pathways. And within our body, we have lots and lots of metabolic pathways functioning together. So we have some metabolic pathways that break down fuel molecules to generate energy within our cells. We have some metabolic pathways that make things within cells, so things such as lipids within cellular membranes. And we also have other metabolic pathways that function to degrade or break down things which we call xenobiotics or drugs. So as we can see, the kind of coordinated activity of all of these metabolic reactions forms a really complex network. And this complex network can be really difficult to study and really difficult to visualize using a two-dimensional figure, such as a figure from a textbook. So what our project is working on is translating these metabolic networks and working to visualize them in a virtual reality space. So I'm going to stop here and let other members of our team discuss and present the details of what we've been working on. Bye.
I'm Jen, and today I'll be talking about the design process for 3D metabolism. So we began the design process by asking a very simple question. What problem are we solving? We knew that students struggle with learning about metabolic processes, especially when these processes occur in different places and in different times. So our proposed solution was to create animations to help students understand where processes occur in the context of the larger system. So as a new member to this team, there was a period where I had to familiarize myself with the tool. The design process began by simply understanding the domain. Our team took on the role of a novel learner and began learning basic biochemistry concepts, like what cofactors are and what metabolic processes are. And once we got an understanding of the basics, we graduated into understanding what components were involved in each animation. We mapped every step in the script to a when and a where. Effectively, we mapped each step to the objects involved in that step. And storyboarding helped to provide a common language across all of our partners and to ensure that everyone was kind of on the same page, which became really important when given the multidisciplinary nature of this project. So to assess our designs, we'll set out to conduct a series of usability tests to see how well our designs help students with their learning goals. And for this, we had two evaluation goals in mind. The first is, how effective is the visual design at identifying where electron carriers and complexes are? And two, does the system provide enough feedback to identify key aspects of electrons and electron carriers at different animation stages? So starting next week, we'll be getting feedback on our current designs and making design recommendations for future iterations of 3D metabolism.
Hi everyone, my name is Halen, and I'll be going over some of the work we've done on the prototype this term. So first I'll talk about the evolution of the prototype, and then I'll go into detail about some of the work we've done, and then we'll talk about some of the key takeaways that we've learned from prototyping all of this out. So here's what the project looked like at the start of the term. You can see that it was built in A-frame, it's all web-based, and here's what we have now. So you're probably like, what? What happened? Why does it look so different? Well, we switched to Unity, and there's two main reasons for that. First is we wanted to take advantage of their built-in animation system, and because of that, we wanted to rapidly prototype. And there's a lot of built-ins that Unity has that we just couldn't do in A-frame, or it just took us too long. And so here's some of the core things that we made. This is animation 1. You've seen it from the Figmas that Jen made. So I'll let you take a closer look at that. And then here's animation 2. So as you can see, it's pretty seamless, very easy to make. It didn't take too long, and this is basically impossible in A-frame. And so some of the key takeaways we have are that for general, rapidly prototyped projects, you want to use Unity because there's very easy animations, and it's very easy to port over your Blender files right away and edit your assets, use shaders, things like that. And it's just generally, really quick and really fast for conceptualizing your project. Whereas for A-frame, it's better if you want to make a polished 3D project. And that's because you have a high level of customization. You can add shaders too using WebGL. And it's really easy to ship and deploy. It's a node-based platform, so you can deploy it, you can host it, or you can use something like Glitch to easily share it with other people. But at the same time, it has a very demanding tech stack, so you need to really plan out what you're going to make. For example, we had to change a lot of our data structures to have some of our animations that we were trying to build in there. And there's a lot of scalability and performance requirements that you just don't have in Unity.
Hi everyone, my name is Nico and I'll be going over 3D Metabolomics database. The ultimate goal of this project is not to visualize just a small subsection of what we consider the metabolic network, but the whole thing. For that reason, storing the information we use to generate the network needs to be done in an easily expandable format. With some guidance from the UBC library, we are working on a Wikibase instance that will contain this information in a format known as RDF. Building such a corpus requires scripting Sparkle queries and formatting using scripts. These scripts are still being developed. The left side image here is a similar visualization in the WikiPath project, which is a collaborative curated set of 2D metabolic pathway visualizations based on an RDF model. On the right are some screenshots of our very own Wikibase instance, where we are developing our data model.
Great presentation, guys. It's amazing to see how much this project has come along. So next up, we have the Electrocardiography Visual and Classification Project, or the Ecg Visualization. It essentially brings data visualization to VR. The project offers a novel way to explore ECG records in 3 dimensions, making it more convenient to review and analyze.
Hi everyone, my name is George, and I will walk you through my Ecg Visualization Classification project. So right off the beginning, we're going to discuss the initial idea and how we came up with it. Here is the typical Ecg diagram. It is essentially a 1D signal which measures the voltage across certain nodes on the heart as a function of time. In each cycle of the heartbeat, it has high peak with small valleys besides. All of them needs to be regular, and they will be checked by a doctor to make sure they don't have any heart-related disease. Typically, a doctor requires 30 minutes to 8 hours long of ECG data for medical diagnostic purpose. The traditional ECG data is built in a 1D format, which can only display 1 minute of ECG on one screen. What can we do to fit 8 hours of ECG on one screen? So we came up with the idea of developing an Ecg visualization classification project under VR environments. The main goal of this project is to develop a data-driven ECG diagnostic tool using machine learning for cardiologists. Here is the approach we are using. First, we convert the 1D ECG data to a 2D image, and then import the 2D image into Unity to become a 3D terrain. All the pink peaks and the purple valleys will be aligned in 3D image. We will see the picture displayed in Unity later. After that, we process the image to eliminate and reduce the noise and create an interaction platform under VR environment. Here is the snapshot from Unity to show what we have done. The 1D signal is converted to a 3D image in Unity. Look at the gone ridges. They are properly aligned in Unity, and they are the pink peaks which was shown in the previous image. The 3D image has over 3,000 rows, and each row has 6 cycles. It can easily display 30 minutes of ECG data on one screen, and it helps the doctor to review and analyzing the data more efficiently. In this term, I have added some additional features to this project. The first one is using the Unity graph shader to apply the color bar over the whole terrain set. It shows different colors based on the height, and it helps the doctor to have a better visual assessment over the ECG data. Another feature is to display the anomaly detection over the terrain. I was using the regression analysis, which is one of the machine learning models, to identify these cycles are not aligned with others. So doctors can easily target the area which requires more attention. And now I'm going to invite Kate to introduce the UX design we did in this term.
Thanks, George. So to further build upon George's model in Unity, we decided to create a prototype for the possible interactions a user could have with the terrain. We made a state diagram to plan out how we wanted our interaction to look like, with our goal being to separate the terrain into 3 different sections along the x-axis and to have a different ECG image associated with each separate section that the users could selectively view. So first we started by separating the ECG model into 3 ranges along the x-axis: the first half, second half, and third half as seen in the state diagram above the arrows. And we assigned a different ECG image to each of the 3 sections, so picture 1, picture 2, and picture 3. The interaction we worked on was for a user to be able to click on a section and display the corresponding ECG trace image, and be able to exit the image and return to the terrain and back to the no picture state by clicking anywhere outside of the image. For exiting the image, we also implemented an additional action, which was right-clicking anywhere on the screen. This would be to account for, let's say, when the image encompasses the entire screen, and there isn't any place we can click that is outside of the image. This additional action would allow the user to still return to the terrain to select for a different section. And on the next slide, we have a short video of what the implementation of the state diagram looks like. So first we would be clicking on section 1, which is the section of the terrain that is closest to the camera, and this would show the first ECG trace image. Then we would be clicking on the section that is in the middle, which shows a different ECG trace image as picture 2. And lastly, we would be clicking on the farthest section of the terrain, which would show the third ECG trace image. The next steps for this project would be to implement the UX design with real ECG data, as well as apply convolutional neural networks for diagnostic purposes.
We are now nearing the end of our presentations, so please do remember, if you have any questions, to leave them in the chat for our Q&A session after. Next up, we have a series of presentations from the collaborative prototyping courses. This includes the aforementioned 3D Ancient Athens project and the Virtual Land Allotment and Digital Dreamplay projects. Digital Dreamplay explores real-time technologies such as OBS Studio and open-source live streaming software for live performance. It enables theater productions to show more actors on stage while still keeping physical distancing.
The collaborative prototyping course offered through the Department of Theatre and Film by Dr. Patrick Pennyfather featured 3 projects that were integrated with the Emerging Media Lab. The course featured human-centered design strategies, hybrid agile processes, and different types of prototyping, challenging learners to problem-solve together, working towards tangible artifacts as a key component of the course. Learners took on 3 projects proposed by UBC faculty: Tom Schult from the Department of Theatre and Film, Kevin Fisher from Classical Near Eastern and Religious Studies, David Gardner and Daniel Justice from First Nations and Indigenous Studies. Projects included an interactive remote course toolset, real-time technologies for performance, and an interactive web-based land simulator. The course will be offered yearly in Term 2 of the winter session.
2D maps and photos used in textbooks don't fully convey the topography of ancient Athens and the important spatial relationships among the buildings. So, this semester, we developed a proof of concept for an educational web application that would allow students to visualize historical monuments in their proper landscape.
Unlike PowerPoints and textbooks, the product provides accurate 3D visualization of the location you want to teach or learn about. With the time period switch feature, students can jump back in time to see how things looked in the past, and even compare the past and present side by side. A bookmark feature allows students to save activities or readings they like, and easily find them again later. Giving the student a chance to walk through the city as if they are really there, the product gives a full understanding of where everything is located.
As a team, we have been working hard to prototype what this application could possibly look like, and have included a mock-up in the presentation that we will be testing on students. We hope our work will help the EML successfully implement and build this project in future.
Regulations and restrictions have greatly affected the theater community, leaving many performances on hold indefinitely. Theater creators have turned to amateur online presentations. The virtual DreamPlay presents a new, innovative, and robust way to perform theater online, enabling creators to work together from afar. The virtual DreamPlay is a method for producing and presenting theater online with integrated tools for the stage manager. We present a new yet familiar stage management experience using video streaming tools such as OBS and Stream Deck to overlay and mix actors and special effects in real time. This method allows the audience to be immersed in a play that has face-to-face performances with both actors and audience members abiding with social distancing rules. Using our free and published documentation and a few open source and accessible tools, anyone can mount a high-quality production with nothing more than a computer and cameras. This distributed model means that theater is no longer limited by pandemic restrictions, borders, or expensive and complex workflows, and has the potential to bring performers across the world together.
The Virtual Land Allotment project is being created for a specific Indigenous community to help them better visualize information about their family's allotments throughout time based off of the original legal documents. The secure, interactive web application that we are creating is easy to follow and intuitive, and features a timeline slider that allows users to access sensitive information with confidence. The problem of the original legal documents is that they are difficult to access and interpret, which is solved through the interactivity of the maps on our application.
Super cool to see all the collaboration between students and faculty. Thank you all for your hard work. Now, last but not least, we have Main Mall Hustle, a cardboard VR viewer experience that drops you right in the middle of the UBC Vancouver campus. So to all the people who are missing campus life, this one's for you.
Hello everyone, I'm Zara. I'm a work learner student at EML and I had the opportunity to be part of this interesting virtual reality project, Main Mall Hustle, this term. Let's start with an overview of this project. Main Mall Hustle is a cardboard VR viewer experience that drops you right into the middle of life on campus. The purpose of this game is for the user to get from one side of UBC's crowded main mall to the other side in time for your next class. So basically, the goal of this project is to experience UBC Vancouver campus without physically being there. So it can be useful for prospective students or first-year students who are still confused between different buildings on campus. Before talking about objective of this project, I want to quickly show you how this game works. As you can see here, you can go from one side of a main mall to the other side, while you can see different buildings, and these students are crossing, so you should avoid hitting them because the timer will decrease by -1. And the purpose of this game is to get to your class as fast as possible. And let's go back to objective of the project. The objective of the project this term was to improve the loading time using different techniques in A-frame. The main problem was the slow loading process due to large object and material files using A-frame. We made improvement by using a technique like lazy loading, object pooling, and timer, which I'm going to explain in more details. Let's start with lazy loading. Lazy loading loads 3D objects if they are visible for the user. So how does it work? So we first have to adjust FrostDem as our viewport observer so that we can use this viewport as the visible 3D portion that user is able to see. And then using set attribute, we can load object and material components based on different IDs. So we only load files which are visible for our user and not all other files at once. So what do I mean by IDs? In JavaScript, as you can see here, we can have different IDs like boba, coffee, and Timbits. And then using set attribute, we will load corresponding material files related to each ID. And also you can see viewport here. Moving on to object pooling. We use object pooling for students who were crossing from one side to the other side, which are our enemies of our game, right? So object pooling gives us a reusable pool of entities to avoid creating and destroying the same type of entities in a frame. As you can see here, we are using mixin, which is helping us to initialize the entities of the pool. For example, geometry, material, and position of the students who are crossing from one side to the other side. So each pool can have different size. For example, in our project, we had the size of our pool is 10. And we randomly decide which student image is shown when we request entity from pool. To do this, we implemented a QData structure to store references to students in object pool. So we won't load more students than our pool size. And finally, we improved the performance of timer by running it in set interval instead of tick function, so that the timer calculation repeats continuously at that specific interval. What do I mean by this is, instead of running this calculation in tick, we are using a set interval, which gives us this option to set this time ourselves. For example, in this case, it's 1 second. And finally, the conclusion, as you can see, loading time decreased by 65 to 70% for material files, which is a great optimization. Thank you so much, everyone, for listening. I hope you enjoyed hearing about A-frames and this project.
Thanks, Zara. That's a big performance boost. Thanks, everyone, for your presentations. Now, let's open it up to a Q&A session. So for our first question, and this is directed to the ECG team, the person asked if you guys are doing the image processing directly in Unity.
Hey, Natalie, I will take this one. So for the ECG projects, all the image processing is done in Python and MATLAB. And then the image, after the image is processed, it will imported the data into Unity. So the Unity is sort of a data visualization tool. And also we're building the user interaction platform on top of the Unity. Yeah, hope it answered the question.
Thanks for the response, George. They followed up with the question if you can expand on the Python to Unity pipeline.
Yeah, so I'm not sure about the Unity pipelines, but I can definitely look into it, see if I can streamline the whole process and make it more smoother.
Great, thanks. So our next question is directed to the Faucet Finder team. They asked if it could be used for any other applications.
Well, right now with Faucet Finder is very domain specific. Specifically, the Faucet itself tailored for a course in the dentist faculty of dentistry. But as I think we mentioned in the chat, Dante and I have taken the process of mapping and exploring 3D spaces, taking that framework as well as the code architecture, and we're attempting to generalize it to any 3D space. Because just recently, I was having a conversation with our lab supervisor. Just because we made a film with Faucet Finder doesn't mean we can't use the same processes for another particular domain. So it seems kind of abstract, but the answer is we're attempting to generalize it. But yeah, if you have a more specific domain, I can speak more to that. Or did you have any other 3D space you had in mind?
I'm sure that if anyone has any follow-up questions, be sure to send them in the chat or through the Q&A function, and I could convey that to Julia. So thank you for that. Our next question is to the Digital Dream Play team. Can you have virtual puppets composited into the play as well?
Yeah, absolutely. So a decent part of actually the development of the workflow for creating the OBS streaming setups that would be used to composite actors together is actually compositing also pre-recorded 2D and 3D assets. So we've worked on figuring out how to make transitions between different scenes work smoothly. It could also be the case if you have footage that has a chroma key, essentially basically just a green background around everything but the asset that you want to show. That's also something that could be included on top of the scene setup for where the actors are positioned.
And another question for the Digital Dream Play team. What has been the most difficult in-person aspect of a play to replicate virtually?
That's a really good question. I would say the most difficult thing to figure out has been making sure that the perspectives between the different cameras are all showing up properly when composited. It's about angling the camera properly, and the other thing is also making sure that the transitions between the scenes are happening smoothly, so you don't end up having actors just pop into the scene while there was another actor already there. So just smoothing things out in that sense.
That makes a lot of sense. Thank you, Dante. For our next team, this is directed to the Ancient Athens team. Where does the map data come from?
I can answer that question as well. So it comes from a tile set that's made publicly available by Mapbox. So as part of the SDK that we used for Unity, it comes with already the IDs for those tile sets included. There is the potential to make custom tile sets for a Mapbox SDK, but there are some publicly available ones that I think use pretty similar data to what Google Maps is using. I'm not sure actually if they're the same, but yeah, publicly available Mapbox tile sets.
So for our next question, this is directed to the Main Mall Hustle team. How are users controlling their movement and direction in the game?
So I can answer that. So while you're playing the game, you can control it with your mouse or basically movement of your hand. You can direct your way.
Thanks for the response, Sarah. This is another question for the ECG team. Do you guys use any cloud platform?
Not at this moment. So right now we're using the sample data provided by the UBC hospitals. So we're analyzing like the data for a couple of patients first to see how it works.
We have a follow-up question on the Digital Dream Play project. Maybe Dante, you could answer this. What happens if the cameras aren't aligned right?
For the Digital Dream Play project?
Correct.
Yeah, so if the cameras aren't aligned properly, then you'll get perspective problems when trying to composite different actor feeds together. So it all really matters. The thing that really matters is the way that the camera angles against the ground, because if the angles are slightly different between different actor feeds, then there'll be like difference in sizes for the actors when they're supposed to be the same size. And sometimes this can be beneficial, but in most cases, figuring out where exactly the actor is supposed to stand so that they have the right perspective when composited with actors that aren't actually right next to them. So yeah, just like differences in perspective can cause things to appear incorrect sizes, essentially.
Well, I hope that answers your question. Next we have, this is for the 3D metabolism team. So for the metabolism project, how much customization or interactive effects are there? Say, could you showcase a metabolic genome doing its work in metabolizing, my bad.
Right, so the visualization that you see in the 3D Metabolism project is based on the idea of nodes and edges, where nodes represent metabolites and edges represent reactions between two metabolites. So if you can encode the interaction that you mentioned in the context of nodes and edges, then absolutely it can be represented by 3D metabolism. But I understand that there's also some situations where the places where metabolites are moving between, like for example, electrons moving between different stages in the electron transport chain, that's something that requires kind of a divergent solution to what 3D metabolism not is designed for, but is most convenient to implement in.
Our next question is for Main Mall Hustle. Where did the buildings in the game come from?
That's a really good question. So the buildings in the game actually are taken from, there's a Blender plugin, and in a previous showcase, I talked a little bit about what the process for doing this looks like. But essentially, you take 3D models that are downloaded from a Blender plugin that takes also map data, and taking images of the buildings themselves, and kind of in Photoshop making the UV map of the 3D model that you got from Blender match up to the pictures of the building that you took themselves. It's not a quick workflow. It's actually quite work intensive for each individual building, but I think it results in pretty nice textures for the buildings.
Yeah, and we have a follow-up for that question. How did you ensure all the visuals are loaded efficiently in Main Mall Hustle?
That's actually part of the work that Zara did for this term, is making sure that models and materials don't get loaded more times than they need to. The lazy loading aspect helped a lot with that as well. Yeah, so it's really just about making sure that we are controlling at which stage the different visuals in the application are loaded. I'm glad that you see fast loading. That was actually not the case before this term.
And another follow-up question, what parts of Main Mall Hustle were the most difficult to create 3D images of?
I would say the most difficult, and thankfully not something that we had to do this term, would have been texturing all of the 3D models that you see in the application itself. I think like if you take a look at all of the different buildings, you can see that the textures actually look like what the real building looks like. Each individual 3D model for those textures was curated by students at EML.
That's really cool to hear. Can we play this game yet?
I can put a URL here on the chat.
That would be great. Thank you. And for our next question, this is for the Digital Dream Play team. Are there any lag or bandwidth requirements? And does it require a fast connection?
Yeah, I'm happy to answer that one. Definitely latency and lag are a major concern in a project like this because of the way we're doing it. All of the actors who are involved are local. They're actually all in the same space, so that helps a little bit. But we're interested in seeing when it's further removed how those issues play out. But lag is definitely a key factor in how the actors are able to respond to one another. Luckily, as actors, they're fairly flexible and are able to use their own stagecraft to figure out how to deal with that as it comes up.
Great, that's really interesting. On staying on the same project, you use re-recorded actors as well?
Yeah, there are some situations, and maybe I shouldn't be giving this out, but it's in part of the workflow for digital dreamplay, we do include the potential for adding like pre-recorded scenes in situations where it would be impossible or inconvenient to make scene transitions work properly. That's a potential workaround to essentially just record your actors while in production.
One thing that's related to that piece around the virtual dreamplay project is that really, even though it's being targeted towards a specific play right now, one of the things that we're looking at is how do we best accommodate any of the different kinds of scenarios that might come up that would pose challenges in this sort of a remote and distributed theater project or a performance project. So for a lot of the things like that, we're looking at how they can be.
Great. So we are coming to the end of our session. Does the audience have any last questions? If you do, please put them in the chat or the Q&A. We have one question here. Has anyone looked at using the digital dreamplay for developing remote choreography?
That's a great question. We're in the process of talking about, right now we've really been nose to the grindstone with this particular play that we're looking at, but have had a couple of chances to step back and to talk about the other kinds of performing arts where it might be applicable. So we haven't had a chance to dive into that yet, but it's definitely an area that's of interest.
Do the performers all need a good camera in order to be a part of this?
I think it's in some ways it's a double-edged answer would be they don't have to, but of course the quality that you're going to get is going to be depending on each of those sections of equipment that are being used. So you're going to get a better result if you do have good cameras that are getting used. We're using high quality, industrial web cams for the work that's being done for this project. But the underlying technology, you could simply use your mobile phone and the results would be more grainy, but it would absolutely work.
That's super cool to hear. I'm really looking forward to seeing people use that. So I think, unfortunately, that is all the time we have for today. Great job, everyone who either presented today or worked on these projects throughout the term. If anyone still has any last questions or would like to get involved at EML, you can go to our website at eml.ubc.ca or contact us on our social media accounts at ubc_EML. And that could be on Twitter, Facebook, and Instagram. So thank you again all for joining our 2021 annual EML Spring Showcase, and we hope to see you guys again.